you have the strengths, if you look carefully, of the main transition about 4, so roughly a quarter of or what we expect for a single particle shell. Now, several good experiments were related to the decay of tin 100 over the years. And of course, 94, the first experiment we saw actually the decay of tin 100, Schneider et al., GSI at the US. And even later, from not too many events observed, the half-life was reduced with large numbers, but 0.9 seconds, yeah. And the important thing, the beta endpoint energy for the transition. And this was also within 2 weeks confirmed that the identification of this 100 was also made at Ganil. At Ganil was continue, and there was a first measurement of the energy difference between tin 100 and indium 100. This was about 7 MeV with large error bar, 1 MeV. But anyway, that was an interesting experiment here at NSCL. Daniel Bazin and then colleagues came with another measurement of the half. Now, there was I will cite one sentence from the paper. Here we are listing the single particle energies, and that's an interesting thing. G7 half is below D5 half, so G7 half is the first orbital after the gap, and this was new at that time. All of the n equal 51, the lighter nuclei, they have D5 half first and G7 half next, and this is why it's interesting to know that the crossover, and this would be important to have a confirmation of this analysis here, and the low-lying position of the G7 half is very important in M1 and GT properties in this mass region. And we did it. Experiments on the super allowed alpha decay, following the naming by McFarlane and Sivola, namely 109 xenon to 105 tellurium to 101 tin, and with alpha gamma correlation we can interpreting the results with help of our team. We can say that D5 half is actually 172 keV 50 above G7 half, which comes first. And anyway, this was a kind of surprise. If you look for my previous transparency, I was still keeping G7 half exactly where the D5 half was, even because I was under influence of Hubert Grave, who from his own extrapolations and analysis, he was keeping G7 half about D5 half at that time. Okay, so now the great experiment, again, here GSI to 12, so how many? Well, it should be a center. Paper in Nature, and this is really the first decay scheme established for tin 100. So Alec, this was a moment you could open the bottom. You got to open when the decay scheme will be established. This is not a complete decay scheme. There are 5 transitions. This is rare. There is a mysterious X here, which will be probably less than 80 keV, and this comes from this picture again involving Hubert Grave, Frederick Nowacki, and Kamila Shea among the co-authors. What is the main result? You see, this is the half-life box. You are talking here. It's about 1.2 seconds, but if you add up all of this information, you are getting DGT of 9.9, well, with large error bars. And that got and this is sitting on the log FT. If you convert to log FT, this is sitting here. So it's the fastest beta transition on the planet. Yeah? So without consulting John Hardy, they call it super allowed gamma of therapy. John is very protective. Okay, so let's look further. Now, a couple of years later at RIKEN, a big collaboration also involving and Ganil, and obtained 10 times more in 100 events, about 2,500, so 10 times more than Inge et al. At GSI. So the numbers here are more precise. You see, for the decay energy, for the state energy, and for the half-life in particular. So following the same decay scheme, the same lines were observed, gamma lines, yeah, you are getting a VGT, well, 4.4, not 9.9, yeah? and with this error bar. So still allowed, super, yeah. So, and by the way, you saw the number, yeah, it's pretty close to the VGT obtained by Alex in 1994. Now, back to the theoretical predictions. There's a great team of theoreticians here. I saw at least 3 of them at the audience. Oh, something disappeared here, sorry. And you see here that this was quite a work to analyze gamma-stellar decay of 1,500. And these are the results. So you see that the actual calculated VGT strength moved towards the so-called X number, which is here. You see here there are different models, and authors of the audience can explain what these code names means, and some of them you clearly recognize. So, okay, we have 2 leaders here, and they go to this green line. There is only tiny problem, this X number, and again you see Huber-Grave among the coauthors. This is a summary of the mass separator experiment, and indeed, this was exp number mentioned here, but exp in the language of Huber-Grave was meaning extrapolate. So the exp without the quotation mark in the experiment, exp with quotation mark extrapolate. So it's not a bad extrapolation if you compare here with a real experimental number, because there were many experiments in the neighborhood of 1,500 made in the separator. So actually it's not 5.2, which is here, but it's 4.4, which is here at the edge, yeah? But of course there is an error bar, so the story is not done. We have to make it with the experiment with a smaller error bar. So, and this was the final sentence in the 1994 paper. The calculated gamma-stellar decay, so on, show the importance of being able to measure the total decay energy in a TAX experiment, TAX with total absorption gamma spectrometer. It was easy to write because we were actually running the experiment with a total absorption spectrometer, which came from Mike Nitschke. This was the Berkeley total absorption spectrometer operating at GSI mass separator.
But I think you wrote that sentence.
Yeah, in fact, the total decay energy, it's not only the QEC value, but actually it's a strength distribution, of course, which you can get from that. And this is what you see here. There was an attempt by the actually collaboration led by Valencia, but involving also total absorption spectrometer funds from Sept and Symposium. And what you see here, it's an example that actually it works. Yeah, the DITAS decay total absorption spectrometer mounted at the big ribs was indeed working, but and even you can put the gates and so on and see the lines. The lines are known. Because they were known already for many years from his older experiment on 98 cadmium decay. However, I cannot show the T100 spectrum. We had about 1,000 of implanted ions, but of course it's not all. You have to have them in coincidence with betas and then of course gammas. So it was not enough, and we are waiting for continuation of the experiment. And here back to FRIB. So what you see here, this is there are the photos taken during the experiment in June 22, the experiment by Weijia Ong, which was performed with this foreigner modular total absorption spectrometer and 82 selenium. So this is mounted still at the FRIB decay station initiator. It got enhanced, very nicely enhanced actually, because we got this final module contributed by Warsaw, University of Warsaw, and this is a segmented model. So now we are segmented, and that's important because we can look also for low energy transition, individual transitions, without adding them up to the other one. This is a nice proof. This is the PID, particular identification plot, which has 50 scandium. We had this nucleus at Ganelli in around 1998 or 7, and there were papers about 9 isomers in the nickel 78 region from this experiment, where we had number of isomers, and this was one of them, and now this serves as a let's say nailing for nailing the PID. and as you see, it was enough to run 1 hour with a short gate to get this nice line in the total absorption spectrum.
2 minutes.
Perfect. So what's now? Well, MTAS is ready for its mission at FRIB, and we have accepted FRIB day 1 proposal to study 100-team decay with MTAS. And this is what we expect. We expect these pictures with about 5,000 ions of implanted 1,500 inside the MTAS into our implantation decay stack. And well, of course, more is always better, but this was the amount which was allowed to be listed at the proposal for day 1. And this is the picture. So Marek Karny, our collaborator, assuming that the Hinke decay scheme is correct, the same lines were confirmed in Riken. So what you see here is the decay to 1,1 plus state, but actually the line is about 2.6 gamma, but here you are getting 2 times 511 because this is mostly a beta plus decay. So you are adding 1022 to your original gamma line, because what you see in MTAS, it's the level, it's the level now shifted with the annihilation radiation. And here is the same level. So here you see original energy, but this is after electron capture decay. So we do not have this 2 511s. But what we have we will have one day, we have a ratio of electron capture to beta plus taken with a good stability. Most of the statistics is there. If indeed it is only one state, very likely it dominates. And then we have, of course, the decay energy and of this beta transition. So we have an independent method to test it. There was a mysterious X in the Hinke's decay scheme. X was about 80 keV at the very bottom. There was a series of M1 transitions going down from the 2 plus states down to this expected 6 plus ground state of 100 indium. So here we are showing with our central module how the low energies will look like. Of course, at some moment here, it's not only a sensitivity of our apparatus, they are converted transitions. So most likely this low energy transition, you should look for having a very good conversion electron detector. Remember, you are stealing about 30 keV from the gamma transition, yeah, and this is what it is. So let's hope we see it. So, and the very last transparency. Interesting enough, in 1994, to celebrate the observation of 1,500 and probably of our publication, Alex, Taylor Flatger Fonseca released a limited edition of Porto. And here it is. This would be a great moment to offer it to you, but probably it will be politically incorrect. So I think this you can see at the evening at the place which is more forgiving. Yeah. Happy birthday, Alex. Neutrons, yeah, like 1,500.
So if you do that experiment, I'll open that old bottle you gave me. You gave me a bottle 30 years ago.
And he's still keeping it. I saw it yesterday.
Any questions or comments to this presentation? Except about the wine and the old age.
No, well, we are here. We want.
Go ahead.
So what error bar do you expect to get on the lifetime of the BGT then from this
Here. No, tell me how many ions I will get from my fridge. Yeah, then I will tell you 5,000. On the 5,000 here, well, it should be definitely better than we have right now. So let's assume the previous result is correct. So we should have the single digits, yeah, on like 0.3, 0.2, yeah, something like that. Because look, we should have a good statistics here for the pretty good definition of the decay energy. Yeah, and of course we are pretty sensitive here. The little secret is we point some 0.1 keV transition, 0.1% transition here, but it doesn't show up. So we are sensitive to about 0.5, I would say, percent. Feeding, yeah, extra feeding if it shows up.
Okay, thank you.
Walter Gutierrez.
Yeah, go ahead. Go ahead, Walter.
Okay.
What is currently the half-life of tin 100? What is the value?
Yes, this is the 1.18, yeah.
Okay,
Here
so
it-
within a factor of 2, what Alex predicted.
Yes. Yes.
Okay.
You see, it's an error of Alex or it's a success of Alex? T94, by the way, this was for 7 MeV, yeah? For 7 MeV decay energy.
Okay.
And
Okay.
the respective transitions, now we know that this the QEC is a little bit higher. And by the way, this energy is almost identical to the first experiment at GSI, because the error bar was larger.
So that's 7 over 7.69 to the power 5.
Yeah.
Correction.
Okay, thank you.
Do a quick backup and then we'll calculation, then we'll go from there. Maxine. Go on.
Okay. The time followed by camera.
All right, so first I would like to thank you for inviting me. Thanks, Alex, for inviting me to give that talk. Now I'm standing between several talks from summities in nuclear theory, as well as an experimentalist. Stand between this and the panel discussion and lunch. So I'll try to be brief. So I've met Alex about a decade ago, a little bit more than a decade ago, when I was here at what was formerly known as the NSCL, working with Dave Morrissey. During that time, I was also analyzing some old mass measurement data that I took when I was a PhD student at Triumph, using the Titan penning trap. So we did measurements of lithium-9. And after analyzing the data, I realized that it was of importance for this A=9 system of the IMEME, the isobaric mass multiplet equation. And Alex was in the same building as me, so I stopped by his office and asked him if he could maybe do a calculation related to this. And I have to say that was probably the fastest theoretical calculation that was ever received. And then we quickly started collaborating on a paper to which I was thinking, oh yeah, we can probably submit that to FISRIFC. And he said, no, you should really try for a PRL. And that was a very good suggestion because it actually went through. And that was just the first moment we started collaborating. We then wrote another paper on the mass 20 system for the IMME. This is all I'm going to be saying about the IMME because I decided not to present any of this, but instead to focus on the importance of mass measurements for uncovering changes in nuclear structure far from it, which is something else that Alex is very interested in. Okay, why does mass matter? Mass is a fundamental property of the nucleus. If you would compute the mass of a nucleus, it's simply just the sum of each nucleons. If it's the atomic mass, you have to factor in the electrons minus the binding energy. As you can see from this relationship, you have basically a direct relation between the mass of the nucleus and the binding energy, which is the energy responsible for holding the nucleus together. And precise masses, given on the left-hand side here, it can allow us to refine our knowledge of nuclear interactions that are basically binding that nucleus. And how do we access to this? We access to this by looking at mass differences between different nucleus. Either nucleus that are separated by 1 or 2 neutrons, or separated by a certain number of protons. And this will really depend on what you're trying to study. Is it the pairing between the neutrons, the pairing between the protons and the neutron, etc. But I will really focus myself for this talk on the neutron. Here is a very simple graph where we have what is called the neutron separation energy. So this is the 1 neutron separation energy of the 10 isotopes. This is simply the difference in binding energies between neighboring isotopes that can also be written in terms of measured masses. There's several features that we can see. So first of all, the first thing that we notice is there's a steady drop in that neutron separation energy. And this drop, if we look at the most simplest formulation for binding energy, which comes from the liquid drop model, comes from this asymmetry term. There's another feature that we can see, and this is this seesaw pattern, where you have even nucleus have a greater neutron separation energy. It is harder to separate that extra neutron in that case, and that comes from that pairing term. There is one more feature that we can see here, and it happens at n equal to 82. There's a large drop going from 82 to 83. And this is basically happening at the neutron shell. And here I have like that very simplistic picture there. So the neutron separation energy is the energy that is required to take 1 neutron out. Okay, so you imagine if you're at 83, it takes much less energy to take that neutron out than if you will have been at 82, okay? But because of this zigzag pattern that we have here in 1 neutron separation energy, experimentally, this is not a very convenient probe to look at. So typically what we look at is 2 neutron separation energy, which is the energy required to remove 2 neutrons. So then you can get rid of this effect. And what I have over here on this left-hand side is basically the 2 neutron separation energies of all known nuclei. And we can see very drastically the neutron shells at n equal 126, 82, 50. There is, based on this 2 neutron separation energy, we can calculate another quantity that get rid basically of this constant downward slope. Okay, and this can be seen as sort of like a second derivative if you want. And it's the 2 neutron pairing energy, or 2 neutron pairing gap, also called. And this is basically the difference between the 2 neutron separation energy of second neighbors. Okay, and then again, if I use that same simplistic cartoon, this is basically the difference in energy across that gap. Okay, so if you take this 2 neutron separation energy over here at okay, so at 82, you have a greater 2 neutron separation energy. If you subtract it from the one over here at 84, okay, you get directly that value, which is that gap in energy. Okay, so you can essentially directly access the size of the gap. Okay, and then you see this when you plot those quantity that D to N values.
Whenever you want to advance.
Okay, so when you plot this D to N value, what you see then is like very nice spikes at the magic numbers. It's similar to what you would see if you would plot the the excitation energy of that 2+ state, okay, that we saw in one of the talk earlier, or if you will look at the ionization energy, okay, for that electron in noble gases atomic system. Okay, so these are the two quantities that we usually look at. All right. So this was mentioned earlier in Alfredo's talk, I believe. So the first basically uncovering of the quenching of a shell was basically found from high precision mass measurements back in the 70s. And if we look at this two neutron separation energy as a function of added number of neutrons, we see at n equal 20, these rapid drops in two neutron separation energy, symptomatic of the closed shell. And what was seen by the group was that once you reach the sodium isotope, it doesn't drop anymore. In fact, it raised a little bit up at the observed. And if we look at the nowadays values of that two neutron separation energy for the n equal 20 isotopes, we can see that in fact it doesn't really go up, and it is instead flattening. Okay, but nevertheless, here this quantity is essentially quenched at n equal 20. Later on, in the early 2000s, what was discovered, again, looking at neutron separation energy, but this time they looked, Tanyata's group looked at the one neutron separation energies, but the presence of new shell, and there was the n equal 16 shell that was found over here in the oxygen isotopes. Okay, so as you essentially go at the lower binding energy, close to the drip line, what you see is the opening of an n equal 16 shell. All right, so for the next part of my talk, I'll be moving to the calcium isotope, okay, which is an isotope chain of high interest currently. Okay, and also this is an isotope chain that Alex has spent a fair amount of time working on. Okay. If we look at this D2N value for the calcium chain back in 2003, like this is what you would see. You will see like the rapid increase in that pairing gap at n equal 20, 28, and people were wondering what was going on as you would increase the number of neutrons, if there would be a new magic number as seen for 16. And so there was several predictions done around that time period. So on the left-hand side, so there's those single neutron separation energies predictions from using different models by several people over here. So I will not go in any details about it. So essentially, there's a GXP F1 and 1A that Otsuka-san and Alex worked on, as well as the KB3J that Alfredo that presented at the beginning worked on. So these different models essentially all predicted an increase in that 2+ energy for n equal 32. They differed for the n equal 34. So the big question was, what is happening? Which one of these is actually, or is there, which one of these like a new closed shell? And in 2013, there was mass measurements done at ISOTRAP, which is a penning trap system at CERN, where the new measurement basically uncover a large drop in two neutron separation energy at n equal 32. That we can see in this plot by the S2N values. And essentially the behavior that we observed very well followed the predictions of both Alex model, okay, the GXP1A, as well as the KB3G. And around that time, this is also when ab initio theory started to become more predominant. Like we can see here, like a couple cluster calculation results that was also following well that trend. Now the question remains like which one of these does a better job at n equal 34? Because we can see there's still some differences there in the prediction. So then in 2018, there was a measurement, tough B-roll measurement done at RIKEN, okay, where they managed to measure all the way down to calcium 57. And their measurement basically uncover another drop at n equal 34, but that drop was not as dramatic as the n equal 32. Nevertheless, okay, they concluded that the n equal 34 was still magic or tough, not as strong as n equal 32. Yeah, 5 minutes. 5 minutes, okay, that's good. And we can see that essentially the prediction, okay, of the KB3G was falling pretty well, like all of those measurements, which is like a fantastic. Unfortunately, the author of that paper decided not to show the results with the GXP1F. However, I believe it will be a little bit lower if we look at the previous plot. And nevertheless, I think this example here of like what is happening at the n equal 32 at 34 shell closure is a very good example of the predictive power that the shell model does have, because these measurements were all done after predictions based on the shell model were done. So later on, so in 2021, so there was a series of measurements done in collaboration between two penning trap systems, the Libit penning trap here at the NSCL and the Titan penning trap with which I used to work. And this is like one of the rare examples where two experimental groups usually compete, decided to join a fort in measuring the scandium isotopic chain. And then this is something that mass measurement can get to that you cannot get to if you are looking at the 2+ excitation energies that only matters for the even. Okay? But with the mass measurements, you can get and see what is happening for the scandium. And what we're seeing is in that paper that Alex co-authored is there is at the scandium isotope weakening of the n equal 32 and the n equal 34 shells. Moving, I think moving into the future, then naturally the next thing will be to see what is happening at the isotopic chains below the calcium. It's what's happening for the argon and the chlorine. That will be interesting for the future. If we continue to look for the calcium isotopic chain, so there is currently a lot of experimental efforts done by a lot of the members in the room here. So first of all, ICO did this like very nice review paper here, looking at ab initio theory predictions for where the drip line for the calcium isotope could happen, okay? Essentially, once you reach S2N is equal to 0, that will be the location of your drip line, predicting around 60, while other, you can see here that other models predict a drip line much further away, extending down to 70. If we look one step further, Ragnar here have this did this very nice PRL studying, essentially making predictions on the possible location of the drip line for several of the lightest isotopes. And we can see here that the calcium isotopic chain, because it's at this like a Z equal 20 closed shell, closed proton shell, has somehow like a boost and can extend much further away than any of the other chain, which I found like to be a striking feature of that chain. And now, moving into the future, if we look at the projected rates of isotope production at FRIB, essentially everything that is colored here will be isotopes that can ultimately be measured using either the Libet, penning trap, or Sept, or TOF bureau mass measurements. So we will be able to essentially get down at the very least to the calcium 60. It might be hard to get to the 70, but there is like the future is bright with such rate at FRIB. The other thing that we can see is we will be able to reach pretty far up for the other shell at 82 and 126 as well. And all of these, the other isotopes of interest that are produced are also of importance for the rapid proton capture process, which is a astrophysical process that requires detailed knowledge of what are the closed shells, how solid they are as you move away from stability, as well as what sort of nuclear deformation we have, which are all very important formations that can be obtained from mass measurement. And I'll move to my last slide. Yeah, if I can. So complementary to FRIB, so there is also in the US another facility that will be able to tackle these different shells, going more neutron rich, especially the N equal 126 shell, and that's the N equal 126 factory that is currently under construction at Argonne. So I have here production rates from that new facility that will use multi-nucleon transfer reactions that one of my grad students did. And so we have actually a few 18 days of accepted beam time at the last class pack to essentially study the weakening of this N equal 126 shell as you move south of lead 208. Because this is a very important shell for understanding the production of the very last peak of the R process. On that, I will stop here because Rabbi is standing up next to me and I'm afraid of Rabbi. Oh boy.
All right. Questions and other anxieties for Maxime? Yeah.
Is there any information in the width of that S2N plot? In other words, it's not a delta function, it has a width.
Oh,
So what's going on just off the shell?
oh, that's interesting. At first glance, I wouldn't think there's a whole lot to say. I know maybe Alex can say something about it.
I just think it's what you expect, just
Yeah.
In fact, if I were making that plot, I'd just leave off the odd even.
Robert, can I make a comment?
Sure.
In one very recent collaboration with Alex, we have moving the calcium, well, the experimenters at Ganil have moved to the neutron proton rich calcium. And it turns out it's because of your figure on double magic calciums. If you move to calcium 36, you will find an extremely a peak in the 2+ and probably in the masses, and in the masses as well. In calcium 36 is larger than the ones at 52 and 54. It is really huge, the peak 36 calcium.
Thank you.
The work of your compatriot Louis Lalanne.
All right, so we'll come to an end of this part of the program then, and we're going to move on right away to the shorter contributions, which are given here under the name of panel discussion. What we thought we would try to do is, first of all, those of you on the list who are here should come forward. What we'd like to do is give all of you an opportunity to share with the audience, with all those who are on the web.
I think yes, the people on the web go first.
Yeah, but in any event, I would like to suggest that you share with the audience some of the market events or results that you would like to share about the impact that Alex has had on the field or on your own personal experience. And so, as Don just suggested, let's start with the people on the web. Please keep the remarks fairly short so that we can share them with everyone. And so, Naftali, would you like to go first? Oh, yeah. Go ahead.
Did you say Naftali?
Yeah, it's you. Go ahead.
Well, I know Alex Brown for many, many years, and we have collaborated many times and wrote some papers, several papers, and his insight into the shell model is great and very helpful. I noticed this talk about the beta decay in tin 100, sorry. And I unfortunately was late. I went to have a coffee. And it was the measurement of beta minus or beta plus in this talk, because the beta plus and beta minus should be more or less the same. And when both channels are open, the beta plus and beta minus, if you look at the RPA calculation, the RPA quenches the Gamow-Teller state. If say you was in the beta minus, you measure, and then the beta plus is open, like it should be in the case of tin 120, they are symmetric. Then the strength should be reduced from a shell model, or if the shell model includes two particle, two hole correlations in the ground state, maybe it should be the same. So it's interesting from this point of view to measure each direction in such nucleus like tin 120. And just to mention, we have written together with George Birch and Zeng, I think, or Zhang, and Alex Brown, a paper about transition, beta plus transitions in nuclei, and mentioned or discussed actually this kind of quenching. So that's my first comment. Another comment is just historical. This meeting takes place exactly, almost exactly to the day that 60 years ago, the Nobel Prize was announced to Jensen, to Gebhard Meyer, and who was the third?
Wigner.
Who?
Wigner, I think.
Wigner, yeah, but Wigner was not exactly, he got the bigger part of the prize, but he was not directly quoted to and connected to the shell model. And so that's one coincidence with this conference. The other coincidence is that on that day, when it was announced, I went to the Weizmann Institute to start my PhD with Yigal Talmi, who's another great contributor. Unfortunately, he cannot be here. Contributor to the shell model. Very well, you understand that. And another one is, of course, our friend Alex Brown, who I want to wish on his 75th birthday many, many more years and work. And it seems that this is really being realized with just seeing how many collaborators he has. So that's my second historical comment.
Thank you, thank you.
Well, Benson, it's your, please, if you turn your microphone on, we'll be able to hear you. And you can hear, there he is. There he is.
Yeah, excuse me. Can you hear me?
Yes,
Yes, we can.
Oh, too bad.
You can prevent it.
Go ahead.
So this has been a really interesting morning for me. I've stayed home mainly because I've become to really love the Zoom business. I think it's fantastic. It's the only good thing that came out of COVID is that I've been taking part in all kinds of things now for 5 years. And when I was getting ready to leave, I said, why don't I Zoom? So that's why I'm not there. I'll see you this evening. So let me say a few words. First of all, 60 years, very interesting, Naftali. That's exactly when I came to MSU to start the program of experimental nuclear physics 60 years ago. And I certainly never dreamt it would end up with FRIB. I was hoping to make it through the first 5 years. Hard times. Anyway, for me, it was kind of nostalgic, the whole thing. It's hard to believe that the shell model of the nucleus occurred when I was in high school, really. And now look what it's able to do. It's amazing. And so much of it is due to Alex. I just say one thing about Alex, and then I'll leave it for tonight. The first time I dealt with Alex on nuclear physics was he was a young guy and at the lab. And I went to Hobson with some questions about the F7 half cell. And he said, oh, you really should go to Alex for this. So I went upstairs to talk to Alex, and then I realized what was going on. He said, oh, that's really interesting. I think I can cover this in a year from now. He already had a calendar in front of him, and this calendar had all the projects he was going to do. And this is about 50 years ago. It's amazing what he's been able to do and how it's grown and grown and grown. from the outside, it sounds like, oh, he's doing the same thing over and over, but it seems to be far from true. It's really remarkable. So happy birthday, Alex, and I'll be seeing all the rest of you this evening at dinner. Thank you.
Not all of us.
Thank you, Walt, and we're looking forward to seeing you tonight indeed. Walter, I suspect you will not be there tonight. Or at least you might be there in spirit, but from Vienna, I guess. Please go ahead.
Okay. Well, Alex knows, of course, that I met him almost 50 years ago in Japan for the first time. We heard his connection to Japan, which is very strong. And in my case, I spent a year there together with Alex and also Jean Sprouse, who was mentioned today also, especially his wife, who taught English to some of the Japanese guys. Anyway, after this Japan stay, I went back to Munich, continued gamma ray spectroscopy in 1F7 half-shell nuclei. And especially we observed these nice transitions in chromium-48, which were mentioned today. And Alex joined me and together with the Japanese series, the Kengo Ogawa, to actually do a complete 1F7 half-shell calculation using experimental two-body interactions from mass 42 nuclei. In any case, this was a complete calculation, and I think most of the work was done by Alex, of course. I could not join him in this effort, really. I supplied sort of the experimental evidence of different spectra in the 1F7 half-shell. In fact, Alex, you probably know, I mean, in Germany, there is, if you want to become a professor, you have to do this habilitation. And this work, together with you and Kengo, was the basis of my habilitation work, which I submitted to the Technical University of Munich successfully. Thank you very much. 50 years later that you managed to put me on the way to eventually become a professor in physics. Now, my own interest at this moment has to do with my involvement in using a technique called accelerator mass spectrometry to measure traces of long-lived radionuclides in all kinds of environments. And one of the main isotopes, you all know that, of course, is carbon-14. And carbon-14 from the early days on, and when I see Naftali Auerbacher, I'm reminded that Igor Talmi 60 years ago was puzzling about the long half-life of carbon-14. How could that be explained theoretically? Now, I'm not a theorist, so I only look at some sort of basic facts. The half-life of carbon-14, if you translate it into a log FT value, it's the most hindered Gamow-Teller transition of all nuclei one knows so far, and there are 700 Gamow-Teller transitions known. And so the question is, how can this be explained theoretically? And of course, I asked Alex and several other people, and eventually a paper came out about 10 years ago by Peter Maris and I think James Very from State University, and they did what they call an ab initio all active nuclei, including calculation, and found a Gamow-Teller matrix element small enough to reproduce the long half-life of carbon-14. Now, this is, as far as I know, this may still be a puzzle to theorists to exactly predict this tremendous hindrance and what is the cause of it. I think for me, or for everybody using carbon-14, I call this really a gift of nature to introduce this tremendous hindrance to carbon-14, because if it would be a standard Gamow-Teller transition, like the one in neighboring light nuclei, the half-life would be only 10 days or a couple of weeks perhaps, but not 5,700 years, which made it so useful for so many applications. So this is my own interest in the theory. Can it be explained really? I think there is one paper out, and this can only be judged by nuclear theories, whether that calculation made sense. I still, as an experimentalist, I still see a factor which is being adjusted to give this very tiny gamma-of-Taylor matrix element, which usually is in the order of 1. And what you need to give this tremendous hindrance is a gamma-of-Taylor matrix element around 2 × 10⁻³ because the square of it gives the transition probability. And that, I don't know, maybe theory is that exact that it can do this.
But that's what I tried to say. If n is equal to z, then there's hindrance by some correlations that are on the ground state. And it seems that the RPA does a little bit, at least, of that. But I don't know whether the RPA is something proper for carbon-12.
An interesting comment by Martin Freer from, I don't know, he's in England at some university. He thought that perhaps there is this, one of the nuclei, probably carbon-14, has alpha clustering structure, and nitrogen does not have it at all. So the decay is hindered because of this complete different structure in simple terms, yeah.
Okay, I think we should, John, you want to comment?
Yeah. I think Sir Elliott basically cleaned up the observation by Jankovici and Talmy that the tensor force basically was causing the cancellation. And the cancellation, it's actually a balance between the central and tensor force. So Elliott had a very nice paper in 1956. And the elements of that are still true, I think, even if you do a very large calculation that involves 3-body forces and so on. 3-body forces contribute over to the spin orbit force and so on. They have a tensor force and all the rest of it. But the other thing is very simple. And the first thing, of course, is that the ground state of nitrogen-14 is it's part of an L = 2, S = 1 triplet. And that's completely inert as far as the beta decay is concerned. So it's the smaller piece, it's the balance between the spin orbit and tensor force. They go in opposite directions. So, you know, the spin orbit force gets in there with mixing with a higher state because the 2 lower states have L = 0 and 2. And in fact, you have exactly the same thing in lithium-6, which has a small negative quadrupole moment. And there it's dominantly triplet S1, but again, it's the tensor force that brings in the small triplet D. So it's the same thing. So it's a very simple thing in my mind, at least.
Okay.
Yes, I think they're right. And Talmy pointed that out, that the tensor force is the main contribution. But still, in his paper, if I looked at it again, he thought it cannot solve the ultimate tremendous hindrance, and that there are some cancellation which you mentioned. Yeah. So anyway, it's beyond me to judge that really well.
That was a paper before I arrived to take my thesis with
Natalie, please. I think Alex wanted to add something. My opinion, it's very easy to get that small. Say 0.1. It's a complete average that is 0.001.
Yeah.
And I don't think any theory is going to give you 0.01 or 0.001. It's just an accident. That's my opinion.
Well, I mean,
it's a fortunate accident, actually.
to some extent, you have some control over the spin orbit force because you have the whole states in mass 15. You have this L = 2, S = 1 triplet in nitrogen. And then if you just tune the tensor force a bit, you get the cancellation.
Okay, I think we should give the other panel members a chance as well. And on my list, Don, you're next.
Okay, I say maybe you want John to continue because that was a comment as opposed to what you wanted to say, right?
Well, I didn't want to say anything. I mean, I've known Alex for a very long time. I was brought to Brookhaven to do essentially what he does here, which is work with experimentalists working on light nuclei. That was Ernie Warburton. And of course, Ernie and Alex have worked together tremendously. And that was partly because Ernie wasn't just a very good experimentalist. He sort of blended into theory once his experimental facilities went offline, so to speak. So all three of us have worked together. Alex is fairly patient because he's been waiting for about 6 years for me to write up a paper on 2 gamma decay CC137. And he's been very nice. He hasn't said a word about it. I think that'll do. Thank you, Don.
Okay, 51 years ago, during the Watergate break-in, I did my first nuclear physics experiment at the Tandem in Stony Brook, and that's where I met Alex, who was this precocious graduate student who was going to graduate in 3 years. Noticed all the graduate students in the audience. I think one of the first theoretical predictions he made that really impressed me, and I don't even know it was ever published or if it was just in your thesis, was predicting the excitation energy of the giant quadruple resonances from the effective charges in the nuclei you were studying. Did you ever publish that?
Indirectly, I think.
Yes. So anyway, we both went our separate ways, and I really went a separate way, but it's deciding that, quark degrees of freedom and exotic hadrons were really important for nuclear structure. You remember in the 70s, a lot of us were doing experiments at LAMP with delta resonances, and even Bohr and Modelson were trying to say that the delta 1232 had impact on magnetic moments in light nuclei. And so I devoted 40 years of my career to trying to see if the structure of the proton changes inside the nucleus, or does the nucleon interaction change inside the nucleus. And my wife gets very upset with me because I tell people this and I say, I've done it for 40 years and I still don't know the answer. And she says, you're really making yourself look like you wasted 40 years of a career. So I'm really glad that Alex did useful calculations this whole time instead of wasting 40 years of his career.
When I saw my name on this list, I assumed I was the past. And so the first comment is it's hard to remember a time when Alex wasn't around. Well, let's go back and see what it was like before Alex. My first paper was in 1965 with a 0.8 of a cubic centimeter germanium detector and a 400 channel analyzer. I looked at the paper, and again, the person with one eye is in command of the land of the blind. All those big fat sodium iodide peaks were suddenly full of static. So I brought along 2 show and tell things. This is the 1958 Review of Modern Physics Table of the Isotopes. That's all we knew in those days. And then for theory in those days, grad students in the 60s were allowed subscriptions to Physical Review for $10 a year. Mind you, our salaries were $1,900, but still, and we could get reviews of modern physics for $7 or $8. So this is my own copy, 1963, and the theory we used was Kistler and Sorensen. And so that was what life was like before Alex. Since Alex, he's done all kinds of interesting things. I come at this strictly from an experimental point of view as a chemist, not a physicist. And so Alex's insight into various structure features that we observe and say, how can we explain this? Instead of trying to understand things, how do we understand what we see? and it would just, Alex is easy to talk to. And so there's been lots of time spent just talking about what we've seen and how to understand it. And it continues to this day. I've had lots of fun in the past COVID cranked down year trading emails with Alex about nuclear structure in the Nickel 78 region. I thought I would challenge to the theorists. One of the interesting pieces of nuclear science, what Suka has described, is the monopole interaction in copper, where the F5 halves becomes the ground state and the P3 halves becomes the excited state. So the question is, what will be present in copper 81 when the valence neutrons are D5 halves instead of G9 halves? How will that width change? Because you see up in antimony, the big gap in antimony 133 that shrunk in antimony 135. And we talked to Alex, I don't know if we ever published or how it worked, but Alex's comment was he could take lead matrix elements and just translate them to tin 132 and out came the right results. So I don't remember if it was ever published or what it meant, but I do remember that you were a bit astonished that what you did up in the lead 2 worked for nuclei around tin 132.
Well, that's the level of detail which I appreciate. Okay, this is an opportunity also for those of you sitting here to add a comment or a question to the panelists for lunch, and I realize it's late, so go ahead. Or if Alex wants to add something. Appreciate everything. Yes.
I just want to say something as someone who's substantially less senior in the field, which is that I really appreciate how much Alex has done for like educating younger generations. I took the nuclear talent course summer of 2017 with Alex, and so basically most of everything I know about the shell model I learned directly from Alex sitting in a classroom in Trento. And so, you know, it's been very helpful, and I really appreciate it.
I've enjoyed teaching those. So I think it's not only when he teaches. Alex just did quite a few calculations, or helped us to understand germanium-74 for one of my graduate students, and she was a bit too nervous of going to ask Alex's questions, and I said, "Well, you should just write him an email." Or she wanted me to see the email first and so on, and to send it. So she sent it, and up came a very nice, detailed answer. Much more detailed, actually, than what I get when I get I'm supposed to understand these things. So, in terms of education, Alex is a master's precious, and hopefully that continues for a long, long time to come. Yeah, and if another graduate student that needs help. Anything else from the panel as well?
Is it possible that Alex says a few words to us, because not all of us will be present in the evening?
Thanks.
Alex, can you say something?
I'm not prepared really to say anything. I've heard all these things, and actually I've heard things I've forgotten about. And it's reminded me of so many things. You know, I started with Walter, probably that was one of the earliest sets of calculations. But just to give you something funny from those days, we published those F7 halves calculations. Walter, can you see me or not?
Yes.
I don't know where you are.
Which Walter?
This is the wrong one.
So So what happened is that we calculated everything and we sent it off to journal in Italy, Nuovo Cemento. And a few months later, it comes back, the proof comes back. You remember that? You remember
Yes.
we were in that room and the proof comes back and we had sent them all this beautiful computer output that was all they had to do was just to copy it and make it into a paper. What they had done, they had some secretary that actually retyped
Every number.
into a new table.
Yes.
All right, well, that was crazy enough, but then we were crazy enough to try to proofread it. And then in hindsight, I realized how these days, how little use that is. I mean, now you can just do these things on your iPhone, right? So anyway, that's a little memory I have from the days with Walter. I mean, everybody here is, telling me some memory, and I appreciate everything I've heard. Brought back lots of memories. In my days in Tokyo, I have been able to travel quite a bit. I have prepared, most of you, I've prepared a somewhat more formal, not technical, more formal thing for tonight. It's not long. People have told me, don't say much. Not long, but it's just some sort of insights. And so I'm afraid the people online will not see it, but maybe they'll have a chance to do that. I don't know if we're going to tape tonight.
can post it.
It'll be video recording.
So for those of you who are not there, it will actually be posted later and you'll be able to hear what will be said tonight. So once again, I thank everybody out there and here, and we'll see everybody back in the afternoon to hear about the future, right? Things that haven't been done yet.
Yes, so we will break in for lunch until 2 o'clock, so we'll be 30 minutes behind schedule, but 2 o'clock we'll restart.
Okay. Did we leave stuff here or?
So are you gonna explain how lunch works?
Oh, yeah, there is a cafeteria across the street. Those of you who are visiting us, there were tickets that were available, and so we'll use the cafeteria. Yeah, we'll make sure somebody's watching this room so that things are ready.
So I need.
Yeah, I was there too.
Yes, they're rolled on.
Just the work laptop? And leave it?